Hi, today I'm going to discuss about an article called the Asynchronous Methods for Deep Reinforcement Learning, which is an extension of the previous article which covered the Deep Q network. So first of all, this monograph came out later than the DQN paper. So naturally, it addresses some of the deep Q networks disadvantages and inherits some of the advantages of DQN. So first of all, a simple recap on DQN is that it's a neural network architecture which overcame the instability, the divergence issue of the neural network being combined, deep neural network being combined with reinforcement learning. So the major breakthroughs that the DQN paper came up with is the experience replay, which is basically replicating. So first of all, by nature, reinforcement learning is has a sequential property. When a robot moves to the right side, it can't cover the data that would have followed by moving to the left side. It only gets the data generated by moving to the right side, which that means the sequential nature, which ultimately led to the divergence of the deep neural network. But DQN addressed that by using a concept called experience replay, which is basically getting a replay buffer, a replay memory, and then gathering as much data as possible, and then performing uniform random sampling to kind of make an environment as doing supervised learning with the IID data. Obviously, it's not perfectly IID, but it's approximating that environment, which leads to better convergence behavior. But specifically, that experience replay also comes with some disadvantages, which it requires more spatial. It has a increases the spatial complexity because naturally a replay buffer is a memory. So as if we're dealing with a big replay buffer, then we need more space in the computer, right? So that could be interpreted as the disadvantage. And this asynchronous okay, so this new network architecture is basically called 3AC deep neural network. So just to give an abstract idea, it's not a complete offline learning setting. The DQN is an offline learning setting because it gathers data as much as possible and then starts learning. But this new method does not follow that offline setting. It can be incorporated with the online learning settings, which is basically get the data, and as the data comes in, learn with it and discarding it. That's the online learning setting. And by doing that process somehow is asynchronously in a parallel fashion, it can achieve stability of the neural network, but also still inherit the properties of online learning. And additionally, it has the advantage of not having to use a replay buffer, which decreases spatial complexity, which is more approachable to people who don't have a supercomputer or who have a limited amount of computing power. So the main idea, okay. The framework, the main two ideas of this asynchronous reinforcement learning framework is that previously this idea of learning with asynchronously with multiple actors and learners in parallel, like it's not exactly parallel, but it's replicating parallel. As we know, with a single machine, perfect parallel cannot be achieved. It's more like as if you think as let's think about a RAM, a random access machine. Then let's think each part as an agent. Then the agent does not do a number of jobs at the same time, but it's basically more like it's using the short temporal difference to replicate, like to mimic action, to mimic to make it look like they're doing it parallel. So, and this approach in terms of the reinforcement learning was thought even before this publication. It's technically not new because it's a couple of years, but still state of the art. But the thing is that they tried to implement, they came up with the idea with separate machines, using separate machines and a single parameter server. So the parameter server is basically the deep neural network parameter weights server. They use a single architecture for that, but use separate machines, which one machine will be, so if we have 5 machines, we have 5 actor and learners. So it's a pretty intuitive way to first implement that concept, but it naturally would have a lot of disadvantage because we would first need a lot of machines, right? Which could be burdensome and require too much resource in many aspects. But instead of implementing like that, this approach came up with instead of using separate machines, we now use a single machine, but now the separate machine, like, okay, so in the previous approach, okay, so the ultimate one goal we want to do is to use multiple actor and learners. Approach 1, try to achieve it by using multiple machines. But in our new approach, the multiple actor and learners becomes the multiple CPU threads on a single machine. So it's much now in terms of computing power, we require much less, which is a big advantage compared to the previous approach. And this has the advantage of, because everything is happening in a single machine, now the communication costs of sending gradients and parameter updates are gone. Because if it was across multiple separate machines, that cost would be significant, but now we don't have it. So this enables using more parallel backpropagation algorithms such as hog-wild while training. So that's the first breakthrough of this publication. And the second one is that now we first know that we now have multiple actors learners, which to clarify this actors learners, it's an actor critique algorithm, which means that the actor is basically the policy itself, and the learner is the basically critique, like assessing that action and learning, something like Q-learning. So as we know, there are several approaches in reinforcement learning, and to categorize it, it's Q-learning, which is basically used a lot as a function approximator for regression problems. And there's another one. The second category could be thought of as the policy gradient, which is basically used for classification problems. So when I say it's for classification problems, it's those, for example, the policy gradient is approximating the usual algorithms that might have been used for classification. So you can think of as usually in machine learning, not deep learning, but ordinary machine learning, we could have used a logistic function to solve for classification problems. It could be decision trees, anything, but now we are using the deep neural network in a policy gradient fashion. And the third one, so this publication is dealing with the Actor-critic, which is a hybrid of the Q-learning regression, and which deals with regression, and the policy gradient, which deals with classification. So it's basically using the policy gradient determine which action to implement. And after implementing that action, the environment would give some feedback, and the critique, which is a Q-learning model, criticizes, like assesses that specific action, and then like it's basically giving an internal feedback. And by using this hybrid model of policy gradient and Q-learning, now because it's hybrid, we can avoid the high variance problem, which can easily emerge when only using a single model, like separately. So yeah, so this publication is using this hybrid model, which is Actor-critic, but in an asynchronous reinforcement learning fashion. And also the advantage of using this multiple actors learners is that it can, when it comes to exploration, because, okay, so try to make this abstract this. We know that with this asynchronous approach, we don't necessarily have to go with the off-policy approach, which is Q-learn DQN. We can still use on policy approaches like SARSA, or Actor-critic, but still can have a pretty stable convergence behavior of the neural network. But on policy, by definition, on policy approaches means that a single policy governing both the update policy and the learning policy. No, take it back. A single policy governing the behavior policy and the update policy. So that was the traditional problem for on policy models, because it could easily get stuck into a local minima because it's update policy and the behavior policy being the same. And the original, so that was the original problem of on policy. And as an alternative for that problem, they came up with an off policy model, which uses a different policies as its update policy and behavior policy, which was Q-learning, right? Q-learning used the absolute greedy policy for its update policy, but uses an epsilon greedy policy as its exploration policy. However, that off policy also has, which was good, but now since we don't use only one actor and learner, we can actually explore, virtually have multiple exploration policies, because we can differentiate the exploration policies across different multiple actors and learners, right? So in this case, we don't even have to incorporate the off policy model. So that's another solution of that was given by this publication. And also, in term when we come to the parallelism in this parallel aspect of this algorithm, basically in the typical approach, we have updated so this algorithm is composed of two parts: the actor, which is basically the policy gradient part, like in layman's term, like which action to perform, the algorithm part that determines that part. And the second part is the critique, which we can think of as the ordinary Q-learning. But if we think about the equation of the Q-learning, it's basically it's bootstrapping. So it's using its next state's Q value, next time steps Q value to determine, to update this time steps Q value with, so if we put this time steps Q value in the left-hand side of the equation, the right-hand side of the equation will be composed of two terms, which is first the reward from that immediate action, and the second term would be the cumulative, like future cumulative total reward. But here, since we're using only the immediate reward, which is only accounts for one time step, this means that we are updating this state's Q value only that okay, that means, to more abstract this idea, the immediate reward from one time step, that's the only factor that's directly updating this state's Q value. All the previous states state action values are implicit in the second term of the equation, which means that they are still affecting this state's update, but it is indirect, it's implicit. So which means that because of that indirectness, the update will not be as fast as incorporating everything directly, which basically requires more computation, and naturally the neural network will converge much slower. So to tackle that problem, now a concept of n-step Q-learning can be used, which now the Bellman equation for the Q value becomes the left-hand side is still the same, but the right-hand side is not only the immediate reward from one time step, but the the accumulation of the rewards from the previous some number of hyperparameter like k time steps added by the maximum cumulative reward from some after k. So by doing that, since now we are increasing the number, in fact, like since now we are updating the Q value with directly with more terms, the neural network will naturally converge faster, and it obviously leads to betterment in the performance.